Okay, great. Thank you for coming to the talk. And here, I think you have learned a lot about quantum error correction code over the last few days. And today, I think I will give you more perspective from a computer scientist. And especially, we will focus on the computer, quantum system optimization, how it evolves from the NISQ era to fault-tolerant quantum computing. And here is the outline of the talk. And if you look at it, we have several components. And the first component is the background and motivation. Especially, quantum computing has been there for over 40 years. So we want to understand where are we now, and what are the important research problems in the next few years, or even 5 to 10 years. And especially with the role of a computer scientist, what kind of research job can we take in that new wave? And the second part, I will use 10 minutes to give an overview of my the quantum system research in my group, and especially I will focus on the compiler optimization topics for the QEC and hardware integration. And then we will give a deep dive into one of the recent papers that is on the qLDPC decoder part. And through the decoder part, I will give you a tutorial to the introduction to different kind of qLDPC code, including both HGP code and the BB code. And then we will dive into the decoder designs, and especially what is the state of the art, and what is the novelty behind our new decoders. And the last part will be a coding test, and you will have the kind of pleasure to play with some of the simplest decoder and try to run the libraries, and so that you can have a hands-on experience. So that's the outline of the talk. Let's get started. So what we know? I think knowing the past is the key to the future, and quantum computing has been there for many, many years, and especially the first wave started about 1983, and at that time, the concept of quantum computing was first originated, and I think one of the focus at that time is try to see if one day, suppose that one day we can really building this kind of no noisy, perfect, large-scale quantum computer. Is that really useful? Or what kind of application can benefit from such kind of quantum computer? So that's a focus of that first wave. And through that, people find a lot of potential useful applications. If you look at it, especially those kind of application with this kind of quantum data in that, for example, simulating the physical systems or chemistry systems, or classical problems with classical data, but with some kind of hidden structure in it. For those kind of applications, it seems that quantum computer can have the potential to give exponential speed up. There are also some problems we know that can give quadratic speed up on quantum computer over the classical machine. So people realize that, okay, even such kind of computer is meaningful. Okay, does that really mean we can build it? Okay, after several years study, especially from the experimental physics, people find that, okay, maybe the assumption is too ambiguous or too ambitious. And especially people find that quantum devices are very noisy. After many years study by the physics, we can only reach about 1%, 0.1% gate fidelity, which is much worse than what we have in classical computer. So if you know classical computer, our fidelity is about 10 to the 10th to 10 to the 15th better than what we have in quantum computer. So it seems that noise is a big killer here, okay? And so that leads to the second wave. If you look at second wave, the assumption about the computer we can build has changed, okay? So now the assumption is one day we can still build a very large quantum computer, but it's not perfect. Actually, it's noisy, okay? But it can be very large, okay? Scaling is not a problem, but noise is not is under our assumption. And the good news is actually it theoretically proved that even one day we can build an only noisy quantum machine, but as long as it's very large, it still works. Okay, it has it's building on this kind of quantum error correction code, and it's called fault-tolerant quantum computing paradigm, and it has two strong theory conclusions at that time. The first one is about the error threshold. The error threshold tells you that as long as your quantum devices is kind of good, okay, at least the gate fidelity or like is below some threshold, then you can use many qubits to working as one physical logic qubits. In that way, you can still like having this kind of like you are having ideal devices, okay, as low as like you can reach as low as like logical gate fidelity as you want, as you are putting more resources into it. And it can also like actually it also tells you that how much resources do you need? How many resources do you need? And does it really breaking this kind of exponential speed up? And the result is no. Actually, for those kind of applications, you show you have the exponential speed up, the resources overhead by applying this kind of error correction code is tolerable. But for those kind of applications with quadratic speed up, that might have a concern, okay? Especially in a reasonable range of the scale, then like this kind of speed up from the quantum computer is of concern. So it seems that now like we are having this kind of theoretical foundation, you may thought maybe we can like try at that age, at that time, maybe we're like the next like wave should be focusing on experimentally proving all this kind of QEC related theory. But it's not, okay? You may think why? Actually, third wave is trying to focusing on the experimentally proving we have some kind of quantum speed up on the existing devices. Those kind of devices are known as NISQ devices. And they are small, and there's no error correction code. And the key idea like here is like, and you have seen a lot of quantum advantage experiments in the last few years, from Google to USTC and to Xanadu. And one of the key idea here is instead of like showing those kind of practical application we found in wave 1 and those kind of QEC protected protocol in wave 2, we ignore all of them. And we are just working on the existing devices. And the reason is even like try to prove anything like in wave 1 and wave 2 that will requires a lot of resources. And soon you will see that data, okay? And it seems that this one, the wave 3, is a more near-term milestones we can achieve, okay? And if you think about it, does really like there any theory tell us like wave 3 would succeed? Okay, give us some practical speed up. No, actually, there's no foundation there. It's more like a machine learning error. Okay, so like so like wave 3 like leads to the NISQ error with a lot of NISQ application. If you look at a lot of NISQ application like the VQA and QAOA, they are really mimic the way of machine learning is working. So a lot of in machine learning, if you look at it, a lot of theory even today like the DeepSeek, the ChatGPT, if you really understand the theory like that, will give you 100% confidence that it will work. No, you don't have that one. You can prove a lot of things, but usually it's first working, then you do the proof, okay? And it's the same like insight behind the NISQ error. So we want to show like whether we can do something meaningful on the NISQ devices, but doesn't really have a lot of theoretical foundation, and meaning, okay, NISQ really will lead to any like practical speed up. Okay, so that's the conclusion. But the good news is, like through these years, about the 10 years of exploring this kind of NISQ error and with a lot of NISQ applications, now we are having the quantum devices with more qubits and higher accuracy. Okay, so I can see like this wave 3 is kind of fork on the road. Okay, you try different kind of things based on your current capability, but through this process, you are getting stronger and stronger. So that's why like I think now we are at the advert of the for tolerant quantum computing era. And the idea is now like I think we have the strength, we have the power, we have the hardware devices to at least show some kind of the practical like quantum speed up with a theory in wave 2 and with the application in wave 1. And but now like we are working on the NISQ, but working on the noisy but large scale quantum computer, the same assumption as wave 2. Okay. And I think, like, especially if you know that recently there are a lot of experimental like achievements. For example, one from Google, maybe you like learn something from Cody like yesterday about the achievement from Google. Like they show that okay, as long as you are increasing the distance of the code, you are using more logic physical qubits to build one logic qubit, you are really suppressing the error. Okay, so that's why like you are showing that okay, quantum error correction is really helping you, and there's a trade-off between the fidelity and the scale. Okay. So I think that is the first prototype. So now the question is, what is our role? Okay, especially if you are a computer scientist like me, I also have a physics background. So I get my bachelor and master degree in physics, and then I jumped to computer science as a PhD. So I really like my background. So I always think talk to myself, what is the unique role of my background and what kind of things I can do as a computer scientist. So what's my difference between a theoretical person? Okay, and how can I bridge the gap between the theoretical person and the experimental person? That is always a question I ask myself. And I think the role here, if you look at it, the computer science, quantum system, as I described it, is more like a bridge between the QEC software and the quantum hardware. Okay, so if you think about that, if you have a really perfect quantum hardware, the topological quantum hardware that can prevent a lot of things, then basically you will need very lightweight QEC software. Okay, but on the other side, in reality, the quantum hardware is not perfect. And actually, we now have a lot of practical quantum computing paradigms or platforms, but now each of them will have its own strengths and drawbacks. Okay, for example, superconducting devices usually have this kind of limited connectivity. Usually, it's in a 2D space with only neighboring connections, and also it will draw it can the dynamic errors, for example, the cosmic ray and fabrication errors also damage the performance of superconducting devices. And on the other side, for example, neutral atom is better because now you can move your qubits around, move your items around so that you can have better connectivity, at least the definition of connectivity. But now the connectivity is brought in by the qubit movement, but qubit movement itself is very time consuming, and the gate kind of latency is also much slower than what you have in the superconducting devices, and similar for other platforms. So in reality, you do not have real perfect quantum hardware, and even you can build perfect quantum platform. My argument is that you don't want to build that. Okay, the reason is usually in the quantum the system research, it's not whether you can build it, or the reason is the more debate is whether you can build it cheaply. Okay, whether if the software solution is cheaper than the hardware solution, we will go with the software solution. Why bother to build a really perfect quantum hardware? Okay, so that is the assumption. And the second one is, if you look at the quantum software, QEC software today, it's very general, and a lot of protocol developed in series, series 2, only give you this kind of a theoretical speed up. But there are a lot of real, for example, the constant factors that whether give you the really real speed up, especially in near term. And here is the data from the from a 2022 paper, and it gives the resources estimation for a lot of applications, and in both the number of qubits they needed and the time the time needed to run an application. And if you look at it, for example, for a lot of applications we have interested in, it really requires over minutes of qubits and from days to years to run an application. Can you imagine that you want to run a quantum chemistry application and it will run for 1 year? Do you really want to wait for that time? No, I think that's one of the reasons why, even we have the theoretical foundations, it doesn't really give you an immediate solution. So there are still a lot of space in the QEC software design. Yes.
Does this graph assume some kind of quantum error correction?
Yes, I think they use surface code for different kind of platforms. And for the topological quantum computing, they have a different, simpler code. Yes. But you can look for more details in that paper. So generally speaking, even we have the software today, it's not really practical. So you have imperfect hardware, you have impractical software. That is the current status. Okay, so what is our goal? Okay, so if you really think about it, there are a lot of manual designs. If you look at talk with experts from IPAM, from different kind of universities, or from Google, you will find that there are a lot of theoretical experts try to design better QEC code, targeting their own hardware. So there are a lot of manual designs. But if you really think about it, and later in the second part of my talk, you will see the real design space is huge. Okay, there are a lot of different kind of parts you can tune with, and if you go with this kind of manual design, like soon like you are out of like kind of energy or out of time, so like. And as a system researcher, we know that in classical computing, we have a lot of automatic tools. And if you know that today, like the ML compiler, like TVM, like Triton from Meta, they are trying to do the abstraction of the design space. And then you have a compiler have like this kind of system design to help you find the best solution. And that is the key to the large scale and a lot of fruitful results in the ML field. Okay, I think we should really benefit from this kind of classical computing. Okay, and here just to give you outline about what kind of design space in our lab we are exploring. And I think if you look at it, we have two dimensions. The first row of line is like what kind of QEC code we want to study in our framework, and the lower part is kind of what kind of hardware setting we are trying to have. Okay, I can explain to you like gradually through this talk, but this is the overall structure. And if you look at it, so here, like for example, from the hardware side, we can have a single hardware setting. Like for example, we're just focusing on the Google superconducting devices with this kind of 2D lattice structure, or like we can looking at the IBM's hardware with this kind of heaven hexagon structure. If you look at a lot of manual designs, they are only focusing on one of the code and also one of the hardware setting to see like what kind of code designs you can explore there. But we are trying to expand that kind of design space. For example, not only one hardware, we can like really like abstract all this kind of hardware as a coupling graph, and then like we can like study multiple different kind of hardware devices. And if you can really think about this kind of like, for example, neutral atom devices, it's not a fixed topology with a fixed connections, but you can move the qubit around, then you can have this kind of virtual like coupling graph, which will change across time. But like during each is this kind of connections, you will have some constraints there. So like with better constraints, you can extend your study from a single hardware to like more general hardware connections. But you know that this one like is a little bit tricky. So what does that mean by generalized hardware technology? So the basic assumption is usually when we like do abstraction of the hardware, we will have a lot of ideal assumptions. For example, like all qubits are the same, and they are really like the noise profile is always uniform, and all this kind of assumption is kind of giving there for that we can better study the QEC code, but it doesn't really hold for a lot of time. And soon you will see the examples. And I would like to thank our collaborators. And so by the collaboration with national labs and also the industry collaborators, we have resulted a fruitful result in the last few years, especially focusing on the QEC study. Okay, so let's first look at the first part of study, and the first it was focusing on like how to map different kind of QEC code onto diverse set of quantum hardware. Okay, so let's start it from that one. So I think I still remember several years ago, like when I talked with experts from Google, and at that time, one of the benefits they claim Google's devices over IBM's devices is Google are 2D lattice. Okay, and if you look at the 2D lattice, each of the qubits can connect it to 4 neighboring qubits. And for some of the reasons, the fabrication yield and other reasons, for example, IBM regarding they do not really having this kind of 2D lattice structure. They have a sparse architecture. For example, for IBM, this kind of like having hexagon devices, like the highest degree is 3. Okay, for example, these qubits were connected with 3 neighbors instead of 4 neighbors in the Google devices. And in this way, they can break like the cost of their quantum hardware lower, and they can build like larger devices. Okay, and the problem like when I talk with the Google's expert is they believe like.
That's all right. It's going great so far.
Thank you. Okay, so like Google saying that, okay, one of the benefits of building this kind of 2D lattice structure is they are future compatible with the surface code. Okay, if you look at surface code, I think yesterday you already learned the basics about the surface code. It requires this kind of 2D lattice structure, and each of these kind of measurement qubits were connecting to 4 data qubits. And it seems that this 2D lattice structure is a perfect match for that one. Okay, so that one, so like one of the theoretical idea is like instead of using surface code, maybe we can manually design some of the code that is better for this kind of sparse architecture from IBM and Google. Okay, but as a system researcher, we wonder, is this kind of mismatch really that serious? Or like you cannot really mitigate it from the software solution? And it turns out that actually you can do that. Okay, the reason is if you think about this kind of QEC code, the key idea is still redundancy. Okay, so you are trying to use a lot of physics qubits to build one logic qubits, and the surface code just to tell you like one of the nature way to do that. Okay, and actually you can really bring more like redundancy into your code design so that you can really release this kind of constraints on the degree, qubit degree. And in our paper, you will see more details. But the high level is our solution will let you to map surface code to any of this kind of superconducting hardware topology. Okay, we are really only describing this kind of hardware connection as a coupling graph so that you can study the way of how matching a surface code to different kind of hardware. Okay, and I still remember, like after 1 year, I think there's also a paper from Google that manually studied how to map surface code to the heavy hexagon structure. Okay, but our framework is automatic, and the difference there is in here, I think we put on more when we design the automation metric, we are putting on like the number of CNOT in the circuit way higher than I think there is a trade-off between the scheduling, how many CNOT gate can be scheduled in parallel, and how many CNOT gate you needed to execute it for the syndrome extraction. And if you look at Google, that manual design paper, I think they design a different kind of trade-off there based on this two metric. But the idea is if you have automated optimization framework, you do not need to manually tune for each of the designs. Okay, you can automatically have the solution for all different kind of designs that really give you a better idea about what is a mismatch between a code and the hardware and how that result will turn to the final performance. Okay. So after that paper, we are considering what's the difference between a surface code and any general QEC code. If we can work for surface code, can we really really generalize it from surface code to any stabilizer code? Yes.
Before you leave the previous slides, do you need to? I guess you have to insert swap gates, right? In some.
We are using
some of these architectures, but do you have to?
That's a very good question. I think we also have the solution here. The key idea, we are not really using the swap gate to changing the position, but actually we are using this kind of oscillar bridge. Okay, so that for example, if you have a 4-degree node, you can break it into 2 3-degree node, so that you still have this kind of full connections. Okay, and that way you can kind of preserve this kind of fault tolerant, and it's kind of this kind of oscillar bridge is not from our work, it's from the theoretical study, but that one is trying to manually find the best oscillar bridge. That our system framework is trying to find the best oscillar bridge, because different kind of oscillar bridge will allow you result in different kind of numbers of CNOT gates. But sometimes you can show this kind of oscillar bridge, but that will break the kind of scheduling of different kind of syndrome measurement circuits. So that's why I mentioned there's a trade-off between these two designs. And in our designs, we are kind of manually design a sweet point between this kind of two trade-offs. And that Google paper is manual design, is only for the heavy hexagon structure from the surface code. But they are trying to, I think they are not using more ancillary qubits, but they have to sequentialize a lot of the scheduling of the syndrome measurements. Okay, that is a high-level idea. I think if you want to know the details, you can go through the papers to.
The result is that you don't use swap gates. You don't do swaps.
We don't do swap. But if you think about it, the ancillary bridge, you're also increasing the CNOT gate. But one swap is 3 CNOT gates, so they are kind of different.
Yeah, kind of a related question. It gets to sort of disentangling, changing the code and the mapping of the code onto a particular
hardware
topology.
Exactly.
But then there's sort of the related question that sort of came up in the early days of this, when the hardware wasn't as good, and you actually had 80% of the qubits work well, and you actually had to map and route around the defect structure. And that's going to come up again as sort of the requirements for error get really lower. And so, so they're not quite the same problem, but highly related, and maybe the solution.
I think that's a very good point. And you will see a very similar problem in the next few slides. And we are kind of handling that problem. Okay, so generally speaking, this one try to extend like what we done for surface code to the stabilizer code. Okay, and we also evaluated on various like QEC codes, like surface code, different kind of qLDPC code, and different kind of hardware topologies. Okay. I think that exactly matches to your question. It's like, our next question is like, if you have a single code, usually like when you design, for example, surface code, its assumption is our hardware is uniform. Okay, everything is perfect. Okay, there's no like special error you know about this kind of information. And in other words, surface code or the error correction code is designed for the worst case. You know nothing about the error profile, and error information. In that case, it will give you a good protection. But in real case, that is not true. And if you smartly extend your error correction code software and your error correction strategy, you can do much better. That's a high-level information, a high-level takeaway I want to give to you. And the first one is like surface code deformation towards dynamic defects. Okay, so that is to see like we are building a. Exactly. So I'm saying like I'm getting there. A very good question. Thank you for bringing that up. Okay, so the question is like, if you, for example, like the superconducting devices, you have the cosmic array, and you have the dynamic errors. Okay, and you know that there are, I think, a lot of national labs, for example, the PNL and Fermilab, maybe, I cannot remember, but they are building their devices underground. Okay, so that they can protect their devices from the cosmic ray. Okay, but that's very, very expensive. Again, like as a software person, as a system person, my argument is if you can solve it from the software level, it's cheaper. And it's cheaper, I believe it's better because you can really put it into practical in a short period of time, and you can draw more attentions. Okay, and even like you can put it underground, you are still like kind of suffering from the cosmic ray, but you are reducing this kind of rate. And our conclusion is if you can. But it turns out that you cannot really protect it from the cosmic ray, so that you cannot affected by them. But you can detect in a cheaper way. You know that it's heavenly and well is heavenly. So if you know that information, you can take advantages of that information and deform your code so that you are not working on this kind of defective region. Okay, this way is much better. If you think about it, more like reactive kind of like naive way to protect from that kind of cosmic array without really thinking, leveraging this kind of location information is try to double your distance. For example, like when your distance gets larger, then you can protect it from longer range errors. But that's not really smart. Okay, and our design is we find that like if you can automatically by using a runtime framework that can take that kind of location information into consideration, you can have a mild, about only 20% overhead, like space overhead, to deform your code so that you can get rid of this kind of isolated, the affected region, and only grow your code mildly to the better region. And we also have a compiler so that it can homogeneously take on this kind of architecture, like kind of deformation at runtime, so that all this kind of upper layer software will not be affected. Okay, so that's a high-level idea.
I have a question.
Yes.
When you remove these qubits, do you have to wouldn't it affect the distance?
Very, very good question. So the question is, if you remove the distance, will you affect the? I move the defective qubits, will you affect the distance? Yes. So that's the reason we will do an enlargement. Okay, so that we can restore the distance. But this kind of enlargement only costs you like 20% overhead. Okay, in the space. That's much better if you keep that qubits there without isolated and naively grow your patch. Okay, if you naively grow it, you will need more space. Okay, taking that kind of information into consideration is better. I think that's a key message I want to convey here. Okay, usually like a lot of strategy is for the worst case, but you can do better. Yes.
And how does removing, it's just an extension of the question, how does removing affect the connectivity? For example, if I have a neutral atom array and I remove it, I guess I could replace it, but you need to have a bigger radius to be able to connect with other atoms, so how does that?
That's a very good question. So generally speaking, here is working on the superconducting devices, and remove that, we are using the gauge fixing theory, and that theory allows you like to preserve this kind of logic information during the deformation process, and also like our deformation strategy will allow you to honor the original connection like this kind of topology. Okay, and then we build that kind of connection like into a set of instruction at runtime, so that we can smartly select the best like instructions to do this kind of deformation, and also it will preserve this kind of logic information.
Aren't you changing your logical state when you make a hole like that?
No, that's a very, very good question. The question here is, like, by this kind of deformation and code enlargement, are you changing your logic state? And in the paper, like, we are based on the gauge fixing theory, and we are do this kind of topology. For example, like the short answer is no. And actually, if you the original state is alpha logic 1 plus beta logic alpha logic 0 plus beta logic 1. The logic state 1 and 0 will change, but the alpha beta will not be changed through this kind of process. So you now have alpha logic 0 prime plus beta logic 1 prime. Okay, but that logic information is preserved. Okay, very good.
How will defect removal like change the nearby stabilizer measurement operators near the defects?
So the question is, how can you change the stabilizers in the nearby one? Okay, very good question. So again, like this kind of changing things is first we are using the gauge fixing so that we know, like for example, you can think about it as a super stabilizers. And the paper will give you more details about like what kind of exactly structure you want to change. And but I want to emphasize two information. So the first one is we are designing a set of instructions so that the instructions will ensure that you are keeping the logic information intact during this process. And the second one, all the new stabilizers will still honor the hardware connection topology constraints. Okay, and for the details of the like, you can look into the paper. Very good. Yes.
So we are dealing everything with software, but every time we include this defect in my new code, my stabilizer checks would change.
Yes.
Right? So every time I'll have to modify my decoding or basically the stabilizer checking algorithm.
That's a very good question. So now the question is, do you need to change your decoder? Yes. And but the good news is, it's quite lightweight to changing the decoding graph. And for surface code, you have the MWPM, right? And it's quite lightweight to do the change. And every like our deformation instructions can be embedded into this kind of QEC cycles. So this kind of software designs and like the additional like software cost will be very low. But that's a very good question. Thank you for asking that. Yes.
Are there any defect structures that are just unfixable?
That's a very good question. So if you think about it, you have a lot of defects, and the defects will be a long-range correlated error, and that is already bigger than your code distance. Definitely, you cannot correct it. Okay, but the question is, like in reality, what is this kind of effect? Like we are using the real like data, I think from Google, like the experiment paper. I cannot remember the details. My students may be the better person to answer your questions. But based on the real like experimental setting, we are showing that, okay, the performance is pretty good. Okay, but very good. Okay, yes.
How fast can you react to these dynamic errors that happen?
Okay, so now the question is how fast you can react to the defects. I think there are some software papers showing like they can. I think the reaction is within several cycles, and the defects will last for maybe several enough cycles. But do not rely on my words for the fact. Refer to the paper. Okay. Yes.
Please correct me if I'm wrong. So, but this surface code will represent like a single logical qubit, right? And if you have like an array of logical qubits, would this scheme present like entanglement between the logical qubits, or like what happens in that case?
Okay, so in short, is the logic information is not changed to for the deformation process. Okay, and for the details, you can refer to the paper. Okay, and it's based on the gauge fixing theory and what are the local instructions we are allowed to have for the deformation process and the enlargement process.
Yeah, so here I saw like you like have an error, you just like expand the code assumptions. But if I know that 2 qubits has an error, I reinitialize it. Can I just reuse them again?
That's a very good question. So your scenario is a little bit different from what we have here. I think your assumption is more like item lost in the neutral atom devices. Usually for different kind of scenario, you have different kind of assumptions. For that assumption is you can reinitialize that part so that you can reuse it. And then you have to take into consideration how long you will take to reinitialize it. And here the assumption is more like you will have the cosmic ray, it will stay there for some time. Okay, and it will like try to grow into its neighborhood. So usually you have different kind of assumptions about how this error can happen. You take that assumption into consideration to build your software. But generally speaking, different kind of assumption will make slightly change to the software you want to build, but you can build it.
So for superconducting, it is not possible to just reinitialize it in the ground state, or
the cosmic ray is more like how the cosmic ray is affecting these kind of devices. It will stay there for how many cycles there. So you cannot immediately really reinitialize it and do the computation. And then like if you want to do that, you will also check with this kind of quantum hardware to see like whether how long that will take to do the reinitialization. Okay, but very good question. Yes.
So after a while, will you check the defect region again to see whether the defect is still there? If there's not there, you can like reuse the qubit so the code can be like smaller. Otherwise, the code will continue to expand.
I think on high level, that's correct. Okay, and here like our assumption is there is a software already there to tell you when it's happening, how long it will happen, and which part can be affected. If you have that information, you can build the software here. Okay, yes?
For a given number of physical qubits, ideally you would want to maximize their utilization by optimizing for the code distance and the number of logical qubits you can build. So for a tightly packed logical qubit geometry, how would code enlargement work?
Okay, that's a very, very good question. Again, if you look at it, our enlargement will preserve about 20% qubits. And that 20% is based on like our understanding about how this kind of cosmic ray error will happen, how long it will last, and how much space we needed so that we can restore the original distance in the presence of this kind of cosmic ray. And after that, we are preserving a range around there, and so that our design and the deformation will preserve kind of like regular structure as a standalone code, and all this kind of like a compiler can be run, can be executed upon it. If you look at it, this is original D, and you have a data D. And you also have to consider, and this kind of data D is shared by this kind of lattice surgery, this path between the logic qubit and the lattice surgery. You have some designs here so that you can better save the number of qubits. Exactly correct. Okay, very good. Okay, we have a lot of questions. I hope you are interested in the paper. So after the class, you can look into the paper for more details. Okay, so the next question I think is almost the same setting. Okay, but now like we have different kind of assumption. So that is now like your hardware is having the drift error. Okay, your superconducting devices for several hours you have to recalibrate. Okay, so if you have an application that has to run for days, so what will happen? Okay, even at the beginning, the physics error is below the error threshold. You know that you can run your surface code so that you can have better error protection. But after some time, for example, after 7 hours, you will notice that actually it doesn't really below the error threshold anymore. Okay, because of the error drift. Okay, on the real like superconducting quantum devices, and here even like shows that after about 1 day. I cannot remember, like over 90% of the qubits. So this is for 1 qubit, and this is like a statistical like assumption about like a summary of all the qubits on your quantum devices. About after 1 day, like all the qubits, or like over 90% of the qubits, like their error is above the error threshold. So then you cannot really run your application. So if you have an application that has to run more than 1 day, like how can you run it on superconducting devices? Any idea? Okay, so the key idea here is, again, like we can isolate some of the qubits that can be calibrated through the code deformation. Very similar strategy as we have applied in the previous slides, okay, the previous paper. But now, like, we are trying to do an in-situ fine-grained concurrent calibration so that you can like try to isolate some of the qubits so that they can like be in calibration along with your like logic program execution. So that's a high-level idea. And it turns out that we only need to have about like 12 to 15 additional physical qubits. So it's very resource efficient, and it's almost give you negligible like impact on the execution time. Okay, so that's a high-level idea. So again, like these two papers, why I put them together is because like when we have the QEC code, usually we have very like bad assumptions. And the bad assumption is good for the theoretical guy because they are tackling the most challenging tasks. And they can show, okay, even for the worst case, we are doing perfect. But in real case, we are, again, like as a system researcher, cost effective and try to do the optimization for the real case is what we want to focus on, okay? And in that way, we have a large design space, okay? So one thing like I want to mention is like even in machine learning today, you know that for a lot of machine learning algorithms, they are based on matrix multiplication. As a complexity guy, like you may wonder like what is the interest for matrix multiplication? That's all three, and you have the strengthened algorithm, you can reduce the complexity. Okay, so that's all done. Like it's even like polynomial. It's not a very difficult polynomial, but that's all the focus of a lot of machine learning compiler and machine learning hardware. So what I want to see here is like for real problems, reducing a constant factor to make it is workable is generally very difficult. That's very messy and very effective in real time. Okay. Okay, so now like let's look at a different kind of setting. I think it's very challenging and very interesting. That's called heterogeneous QEC code. So I'm not sure whether you have learned that kind of concept in the previous like several days of study. But here I want to tell you sometimes you don't want to only use one QEC code. You want to have multiple QEC code. And why is that? So the first one is, it turns out that if you have a QEC code, not only you have to protect the errors with the QEC code, then you have to apply a lot of logic operation upon that QEC code. Okay, and different kind of QEC code will give you different cost of the logic operations. Okay, so that is a concept. It's more like different kind of hardware architecture will give you different ASA instructions. Okay, it turns out that no QEC code can give you like a universal logic operation that is that is low cost for all the operations in it. Okay, so it turns out that some of the QEC code will give you like, for example, the thin code will give you like this kind of transversal like Clifford logic operations. So that is their like that means that this kind of logic operation can be executed very cheap. Okay, but it turns out that, for example, for T-gate, it will be much harder for the thin code. But T-gate can be transversally implemented with a Rand-Miller curve. Okay, so it seems that now you have two separate components on your hardware, and this part can be used for executing one part of the operations, and on the other part you'll be able to execute some other instructions more effectively. So that's one of the reasons why we want to use heterogeneous code instead of using one code. You may want to use hybrid code. Okay, and definitely like we are not the one like building this kind of theoretical foundations. Okay, but like we are the first kind of work trying to bridge this kind of theory into practice. Okay, and the idea is like we are trying to study if you have these two codes and both of them have to map onto a hardware, and you have to enable this kind of in-situ code conversion between these two codes. So then, what is the best way to do this kind of code conversion? Okay, and we are also assuming one like relical like hardware topology, for example, the 2D lattice structure. Okay, if you only have a 2D lattice structure, what is the best way to map even this code and this code and enable their conversion? So that is like our contribution. So we are not stick to the theoretical part. We want to understand like if you bring that theory into like real like hardware implementation, what are the constraints and what are the optimizations you can do in this process? Okay, and we are also building a compiler. For example, definitely you can just use thin code to do the Clifford, and you can use Rand-Miller code to the T. But it turns out the CNOT can be both effectively executed on both parts. Okay, so that allows you to have a freedom to like delay this kind of code conversion because code conversion itself has some cost. Okay, so that brings you like the compiler optimization strategy into play. Okay. Yes.
Yeah. So during the code conversion, are the qubits protected, or they're very good subject to error?
That's a very good question. So the question is, if you do have the code conversion, is there a way to protect the logic information? Okay, and based on the theoretical study, like there are like already some ways to tell you how to do the code conversion. Okay, what kind of operation you need to do to transfer from code A to code B. That whether this process is exactly like for tolerant, there are still some debate there. I think that is my memory, okay? And you can look into the paper as a theoretical paper to get into more details, and maybe I can give you my students' information. But the conclusion is, yes, there are some theory to tell you how to do the code conversion from one code to the other code. I think the basic information we can rely on this kind of supervisor rewiring. Maybe that is a paper you can look into, okay? Yes?
Are steam codes and read Molar codes also distance 3 color codes? Because I see you colored it red, green, and blue there.
So your question is?
Are Stein and read Molar codes also color codes as well?
Yes. Okay. Okay, so let's look at another kind of heterogeneous design. And if you look at the previous design, so we are using 2 codes. Each of these codes will be responsible for some part of the logic operations. So if you think about it, then like you can have different kind of assignment for different kind of codes. Okay, try to see their combination. And here, this paper is trying to use surface code and LDPC code as a combination. And the reason why we are using the LDPC code as surface code is first, they are popular, okay? And we know a lot of information about them. And the other one is, especially for surface code, we know a lot of we understand the logic operation executions. Even for TCAD, we have the metric state dissolution. And for the LDPC code, it's very known for the resource efficiency. Okay, resource efficiency operation. Any design like operations that jumped into your mind? Okay, very good at storage, very efficient. You can store a lot of logic information into a small patch of code. This one, okay, not very resource efficient, but easy for you to conduct some of the logic operations. Okay, memory, compute logic. Okay, so that is a key idea. So if you look at this paper, we are trying to use the surface code as a computation logic, and then we are using the LDPC code as a storage. Okay, so definitely we have to extract the information from the storage to the compute. So this will give you some cost. Okay, so if you look at this paper, after we build a compiler, we find that there's a trade-off between the execution time and the storage. And for example, by applying this kind of strategy, we can have about 6 times reduction on the number of physics qubits. Definitely, LDPC code is more efficient in storage because you can put less space to store a lot of logic operations. But that is not for free. Especially here, because we are not directly doing any logic operation on the LDPC code themselves. We are transferring the information from the LDPC code, from the some logic qubits to the compute part, and then do the computation on the surface code part. So that's why, you also have a execution, increase in the execution time. There's a trade-off. But the good news is, guess what? For superconducting, we are super fast, okay? So we can really trading off the execution time. I think superconducting, the gate latency is about 10 to the 3 times better than the neutral atom. So that's why 3 times is not a huge overhead. But this kind of 6 times reduction in the storage, that's a big thing, okay? So again, a lot of system research, you will find that you are not creating the new things, you are better exploring the trade-offs, okay? Yes?
So how are you realizing the information transfer from LDPC to surface?
Oh, okay. So for this paper, I think it's from IPAM. They have a paper designing this kind of syllabus, try to get in the information from the LDPC code to the surface code. By implementing that, that's not our theoretical contribution.
And where are you doing the non-Clifford computations?
Every compute is on the surface code. This is only for the storage. Okay, so that's why I'm seeing this a different kind of distribution. Previously, we have 2 codes. Each part will responsible for some part of the logic operations. But now, we are pushing everything to the surface code. Surface code is for the compute, and here is only for the storage. Yes?
Well, I guess I have two questions. My first question is, what's the connectivity you need for the LDPC code here? Because you say you do it on superconducting qubits?
That's a very, very good question. Okay, so here we are using the BB code, and soon we will give you the introduction to the BB code. BB code is designed by the IBM researchers in 2023. They have good kind of locality. They only need 2D, like two-layer hardware fabrication. So generally speaking, like IBM researchers believe potentially superconducting devices can implement that.
My second question is, you claim that your LDPC code here you use is linear in scaling, but most of the LDPC codes I've seen are a little bit worse. So, like, what LDPC code do you use?
BB code from IBM.
Oh, okay.
BB code. Yeah. It's 144 physical qubits, 12 logic qubits. Yeah. I think you will see that information very soon. Any question? Yeah.
Since you're using LDPC code memory,
That's a very, very, very good question. I think if there's one company that should investigate on the decoder, is a superconducting devices company, because they are super fast, the gate level. So the time budget for the decoder is limited compared to neutral atom devices or ion trap devices. I think ion trap devices and neutral atom devices, their companies can rely on IBM, Google to investigate good decoders for LDPC code. But our paper also shows a good way to do this kind of decoding.
Oh yeah, I just mean like, because I think in yesterday's like Google's presentation, like
Okay.
if you're not doing like operations, you can just keep like measure it and keep track of the error, and you don't.
But then if you have non-cliff gate, you have to do that, right? You have.
Yeah, so I just.
It's a storage, you do swap gate. You swap the information out. Otherwise, it's not really doing nothing, but the operations you do to this kind of storage is not as complicated as a compute zoom. But you have to still like swap the information out, right? And you have to do some of the swap, like for example, you have 12 logic qubits here with 144 physical qubits. You still have to swap the information within these parts and swap the information to the compute. But definitely, I think the key idea is, if you have storage, and the storage only requires some limited set of logic operation, can you do a better design of the decoder and even like the QEC cycles? Yes, I agree with you. And that's a good research direction. Personally, I believe that's a good research direction. Any other question? Okay, finally, a deep dive into the decoder, okay? So before we go into the details of the decoder, let's have an overview of the qLDPC code. And I think we have a good motivation. The surface code is not good enough. It has a lot of like pros. I think yesterday, if you like learn from the Google talk, maybe you will learn a lot of like good things from the surface code. Especially like it's a simple structure. It's 2D lattice. It's kind of like the simplest structure you can imagine. But it turns out that even like IBM and Rigetti, they cannot have the 2D lattice. They are still using this kind of heavy hexagon. Okay, hexagon. And another good thing is it has a very efficient decoder, the MWPM algorithm. The reason is like if you look at every qubit, it's only connecting two Z stabilizers or like two X stabilizers. So that's why you can easily like change this kind of qubit information into one edge and using some of the classical decoder algorithm like the MWPM algorithm to solve it. Okay, it's very efficient and it's embarrassingly parallel algorithm. Yeah, and the other thing is like that there are a good understanding of how the logic operation should be conducted on the superconducting devices, and definitely there are a lot of implementation already for surface code. But the problem is again like it's not very resource efficient. Okay, and now like the ideal like solution is we still have the simple structure, we have the efficient decoder, and we know like how to do the logic operations. And we just like resolve the last question, the resource efficiency, okay? And that drives a lot of theoretical study to understand whether we can even do that, okay? Whether all these kind of assumptions can be satisfied simultaneously. It turns out that, okay, like I think in 2008 and 2009, it's proved that there's a BPT bound, and the BPT bound tells you like actually you cannot simultaneously satisfy all these kind of constraints. And surface code itself, 2D lattice, like 2D like structures with only neighboring like kind of connections. That's already like the best you can do, and especially tells you that the number of logic qubits, the distance, and their square, their multiplication will be on the order of the total number of qubits. Okay, it seems that surface code is already pretty good. So at least you have to break some of these kind of assumptions. And and the assumption turns out to be these kind of non-local interactions. Okay, it seems that like only like you have to break this kind of non-local connectivity so that you can have better code performance. Okay, so like the LDPC code is trying to like relax this kind of 2D local structure into this kind of low density parity check. So what is low density parity check? It tells you like we do not really require how these kind of connections are connecting to your neighbor or maybe far away neighbors. We only put on constraints on the, for example, on the number of qubits, number of like checks you're connecting to, and the number of qubits for each check they are conducting on. Okay, so that's why like we are seeing this kind of R and C, which R, I think R is like the degree for the checks, and C is the degree of the qubits, the data qubits. Okay, we put bounds on both of these two numbers, and if these two bounds are satisfied, then we are seeing like we are having good LTPC code. And some of the like kind of expectation of the good LTPC code is we have n qubits, and the logic qubits is on the order of n, so that we have really like resource efficiency, and also like the distance is also on the order of the n. Okay, and the good news is like Daniel Gottman in 2013, they also like proposed some of the logic operation implementations on this kind of LDPC code, some general like strategy for this kind of LDPC code, and but now the question is, does really good LDPC code exist? Like, or like we know that potentially there's something there, but can we really create them? Okay, and it turns out that there are, I think the first breakthrough is from the hypergraph product codes. The HGB code is proposed in 2013, and it is the first time, if you look at compare it to surface code, we have n and 1, and now it's n polynomial n. Okay, so that is the first time we are trying to really bridging like increase this kind of number of logic qubits you can present using our DPC code to a new level. But that time this kind of code distance is still squarable, so similar to the surface code. Okay, and later on, like people studied a lot of this kind of explore a lot of theoretical studies, and we have the Leaf City product code, which further breaks the distance from square n to n. And last year, or 2 years ago, like the BB code from the IBM, they showed that, okay, so some of the code, even like they have this kind of polynomial like good performance, but the n can be very, very large, to thousands of physical qubits. So that's hard for physical implementation because the best devices we have today mostly have like sovereign level, like 1 sovereign level of number of qubits. So that's why even you have this kind of complexity level good performance, if the code is too large, then there is also a concern. And the BB code is kind of something like give you the practical parameters from IBM. If you look at it, you are using 144 physical qubits to build like 12 like logic qubits, and distance is about 12. Okay, so that's good news from IBM. And in this talk, I think we will go through the HGB code and also the BB code to give you some high-level idea about how these two codes are designed.
Excuse me.
Yes.
Can you go on the last slide? I couldn't understand why lifted product codes are bad in terms of like scaling. You said that their dependency on n and on on.
The question, my point is, like even you like previously it's kind of high HGB code, they find something there, but it turns out the code is very large. Okay, so n is on the sovereign level to have this kind of good performance. So that's too large for current implementation. So that's my point.
So the performance was not seen like the larger numbers of n.
The current hardware cannot have that number of qubits. That's a problem. So even you have a theoretical things, it's hard for your current experimenter to prove that. That's hard. That's a longer milestone. Okay.
By the way, obviously these all violate the PPT bond, right? But I guess that bond.
No, that's PPP bond is for you only have neighboring.
So that's I was going to say.
Yeah,
that's restricted to a neighboring.
Yeah. So that's why you have to break something so that you can get
relax the neighboring constraint to a bounded distance. Is there any theoretical result?
I don't know, sorry. But that's a very good question. So the question is, is there any theoretical study about if you break this kind of things, what is the best you can have? And from the theoretical study, I think you have n, polynomial n. I don't think you can, if you find a code on that level, I don't think theoretically you can do anything better, right? You cannot have logic qubits more than the number of physical qubits, right? And you cannot have the distance already like better than like the number of physical qubits you have there. So I'm not sure, but based on the study, it seems that you can have achieved like pretty good result. Is that kind of reasonable? Yeah.
Maybe like this bound is parameterized, like maybe you define a certain ratio of the distance, the longest distance allowed versus like the whole code.
Yeah, from the comparison level, I think this is the best you can do. That's my conclusion.
No, but my point is that there's two distances. One is the distance, the code distance.
Oh, the other one is like
the connection distance, physical. Yeah. So when you embed.
Oh, that's a very good question. Yeah, I totally get your point now. So the question is like if you want to limit on their physical connections, like for example, you can like break these kind of neighborhood connections. But you still want to limit on how many steps you want to do the move. Another assumption usually for the neutral item, I think they feel like it's more realistic and general. It's not the distance, but for example, how parallel you can do this kind of movement, okay, so that you can achieve that steps. So that's why I'm saying like system research is very interesting. You can get a lot of different kind of assumptions to build the software for it, so that you can drive the design of the hardware. Okay, okay, so very good. Thank you. So the HTTP code on high level is try to like get the hypergraph product of two classical codes. And for example, now we have two codes, and the first code like is called we call code A. And for code A, we have this is the number of bits like NA, and MA is the number of checks. Okay, can you tell me like how many logic bits are there? NA minus MA. Okay, is that clear? Okay, and for this one, yeah, similarly, like you have another logic code, classical LDPC code, and it's called code B. And here, like we have NB number of bits and MB number of checks. Okay, and this graph is called Tanner graph. The Tanner graph is trying to use this kind of circles representing bits and this squares to representing checks. And if there's a connection between this like a node here, like a circle node and a square node, meaning that this check is checking on that qubits, that bits. Okay, so that's the Tanner graph. And here, like the HTTP code tells you that if you have two really good classical LDPC code, and that is like a good classical LDPC code based on definition. So all three are on the same level, and tells you that okay, first we have a good way to tell you like it's a valid quantum LDPC code. Okay, valid means like all the Z stabilizer and X stabilizers commute with each other. So that's how we know it's valid. And the qLDPC code know that the connection are bounded. We have the RC bounded relationship. Okay, and then like we also know the parameters of the new design code. And the new code will have these two on the same level, but the distance is square of n. So that is the information. Okay. Again, like HTTP code tells you a way to combine two classical codes so that you can preserve this kind of good parameters of the LDPC code, the classical LDPC code. And there's like you have to understand this kind of strategy so that you understand, okay, first why it's valid, why it's bounded, and how these parameters get involved in this process. Okay. And we will go through all this process. So the first thing is when you have two codes, okay? Two codes, then like these are the classical codes. What we build here is a quantum codes. And quantum codes, what we have is we have two parts of qubits. Again, qubits are circle, checks are square, okay? And can you tell me how many other left qubits? It's NA times NB, okay? And the right qubit is NB times MA, okay? So this is the number of quantum qubits you can have, okay? And then like you have two parts, one for the X checks, the other one is for Z checks, because in quantum computer, we have both X checks and Z checks. Can you tell me like how many X and Z checks? XZ checks is, for example, for this one is MA times MB, and this one is MB times NA, exactly, okay? So, and can you tell me how many logic qubits are there? One easy way to do that is we can check the number of qubits in total minus the number of checks, okay? And that will give you Ka, Kb, okay? So that is to see like we are just proving these two parts, okay? So this is the original number of A, N. These two, if they are on the same level, you will get the N actually is N squared on that level. And actually this one is the same as these two times together. So that's why it's also on the N squared level. So that's why you have N and N. But the big N is kind of on the level of the small n squared, okay? So hopefully like you now understand why this kind of parameters are preserved by designing that way, okay? Now the question is, how can you add in the checks? So you now have the qubits, and you have the checks. But now like we wonder like what kind of check, like which check should check on which kind of qubits? So that's why I'm saying like we are adding edges to the Tanner graph, okay? And when we are adding the edges, we have to satisfy two things. The first one is X and Z checks must commute with each other. If they do not commute with each other, it's not even a valid quantum code, okay? So that's called valid checks. The second one is it must be bounded, okay? Bounded saying that if the original like LDPC code is RC bounded, and the new like quantum code should be also kind of like the RC bounded. So these are the two information you have to keep in mind, okay? So let's see how like we are transferring the edges from the classical code to the quantum code. It seems very, very straightforward and very easy. If you look at this kind of checks for code A, we just propagate it horizontally, okay? And for the code B, we propagate it vertically, okay? And here is a parity-check matrix. And if you want to understand it, it's quite, here I'm giving you the dimensions. For example, like for HX, how many checks are there is MA times MB. So that's why like we have how many rows here. And how many columns are the total number of qubits, right? So that's why it's this part times this part, okay? And here like why the first part is HA tensor product MB is because we are propagating this one horizontally. So that's why you're having the tensor product of the charity matrix of QA, this kind of code A. And tensor product, this dimension is trying to do this kind of horizontally, okay? If you propagate vertically, you will do the identity matrix on the left. If you propagate horizontally, it's do an identity matrix on the right-hand side, okay? You can do the proof by yourself, but like visually, it's like conducted in that way, okay? So similarly for the RZ, like for RX, you will find that we have this kind of propagation. So that's why this component. So they are connecting each of the checks to this kind of data qubits. And if you look at this part, it's about this kind of edges. It's propagating from code 2, okay, to this kind of data qubits. And it's propagate vertically. So that's why you have these two in different kind of dimensions, okay? I hope you can understand. You can prove it by yourself, but it's visually in that way. Yes?
I had a question. So if you were to transfer like the parity check matrix into like a quantum circuit model, would it be similar to like the surface code where it's like, let's say, I believe for the X checks, the check qubits are the control qubits onto the data qubit, and then for the Z, it's like the data qubit is like the control qubit acting on the check qubits. Is it like the same way? Translate to the circuit model?
translate to a circuit model. I guess your question is, if you have a stabilizer, how can you measure it? Okay, there are all different kind of ways to do the measurements, right? Especially like how can you do that for tolerantly? There are all different kind of tolerant protocols about how to do this kind of syndrome measurements based on stabilizer. And sometimes it's more efficient. For example, if you look at surface code, if you think about it, each of the qubits were connecting to 4 neighboring qubits. And actually, by the C0, you are propagating the error information around. By looking at that circuit itself, it's not fault tolerant. But because of this kind of zigzag scattering and this kind of error information at different kind of different time steps, actually that one is fault tolerant according to the distance d. Okay, so generally speaking, it's a big topic. And if you have a stabilizer, after you define the stabilizer, how to do the measurements, there are different kind of strategies. And if you look at our previous work on the mapping surface code to different kind of hardware topology and mapping stabilizer code to different kind of hardware topology, is adopting some of the fault tolerance strategies and try to resolve this kind of connection constraints. So it's a big topic, generally speaking. So I'm not sure whether I answer your question.
Oh, I was just wondering, like what the pulses I would need to send to do this.
You only need to have here in this step is getting the stabilizer information. So what kind of parity check information you want to get. So which check is checking out what kind of data qubits. That give you the stabilizer information. This one is X stabilizer information. This one is the Z stabilizer information. After you have the stabilizer information, you can represent it using stabilizer code. And then you have the hardware constraints. You can consider how to map that stabilizers into syndrome measurement circuits. So that's the next step, okay? And here, like again, like the Z is very similar. So Z like, oh, by the way, like why this one have a transpose? If you have that question, why it's not HA, but this one is HB transpose? If you look at it, the reason is now like you are inverse, like this part is for this kind of checks, right? But if you look at the original, like we are changing the data qubits to checks, changing the checks to data qubits. So when you are changing the data qubits to and the checks around, you will have a transpose. So that's a hell of an idea, like how can you get this kind of formula? Okay. So, but you can definitely write down like this one is qubit 1, 2, 3, 4, 4, 5, and you can get that orders, try to get this kind of charge matrix sum. But that is a hell of an idea. You do the propagate horizontally, do the propagate vertically, and you know whether you change the checks from the checks and data qubits, and you can easily write down these two formulas. Okay. But generally speaking, you only like propagate from one code horizontally and vertically from another code. That's a hell of an idea. Okay. So now, like, can we see like whether it's bounded? Definitely bounded. You're only propagating from one code to the other code. You are definitely bounded by the original like information. And here just to give you like how they are bounded. For example, the left qubit is by like I give you like RACA of the code A and RBCB on the code B. You do a combination. I don't want to prove here, but if you think about it, because we only propagate horizontally and vertically, we are not having a lot of like cross checks. So that's why they are still bounded by the summation of either their combinations. Okay, so it's very easy to understand. I have the slides, and if you want to check it, you can check it by yourself. But the high level is they are only do a cross at some place. So that's why they only have their summations, not their multiplications, right? Okay, so that's why they are bounded. Next question is a very tricky question. I think that's the most tricky problem for a lot of like code designs is whether you can ensure Z check and X check, they commute with each other. Okay, they don't say it, but sometimes you will find a lot of code design that is the most important information they are inferring. Okay, and if you look at BB code later, it turns out that this is a critical information you want to have there. Okay, so it turns out that yes, they definitely commute with each other for Z check and X check. Okay, so I give you one example. For example, this X check and Z check, either they do not have any common qubits. If they have one common qubit, must be these two, and they will stay always together. Why is that? For example, if you think about that, only propagate vertically and horizontally, right? If they have a common qubit, it must be this qubit. This is the only place they can cross with each other. And if you cross this one, you know that there's one edge here, and you know there's one edge here. So must be one edge here and one edge here. So you understand that part? So that must 0 or 2 common qubits. So it's an even number of common qubits. If you have an even number of common qubits between Z and X, does it commute? Yes, they commute. Okay, this is a special case. They commute with each other. Any questions? Okay, if no questions, you can also, if you remember, we have this kind of formula. Okay, if you have the formula, another way, like this, the matrix format, another way to check whether X and Z check, you just multiply them together to see whether they have even number of ones. And if you multiply them together, you will find that you have 2 identical terms. Identical terms, when they add together, 1 plus 1 equals 0. 0 plus 0 equals 0. Okay, so that's why you want to add 2 things together. They are the same thing. You always get 0. So they always commute with each other. But I like this kind of visual interpretation better. Okay. Yes.
Where does the hypergraph part of this come in? Because these are just edges, right? They are not hyper edges.
Okay.
So where does the hypergraph part of the name come in?
So they are still like combining like 2 codes. Okay, so I don't know what, you may ask the authors why they have these kind of questions. If you have any concerns about in your mind, what is really hyper, okay? But you can see here like checks were inherited from both directions, right? Okay, so it's a way to do the hyper, okay? So again, like when we see like when you create one of the LDPC code, from the classical code, you have to ensure, okay, good parameters. It's valid, it's bounded, okay? And we have checked it's valid, it's bounded. We have checked the first 2 parameters. And now like the last part, I will only give you the high level idea. So the distance is square of n. Why is that? Square of n is just the dimension here, if you think about it. The reason is, if you look at whatever errors cannot be corrected by the classical code, cannot be corrected here. So that's why the distance will be only the dimension of this part. Okay, what is the dimension of this part? Like in terms of the total number of qubits, is square of n. So that is the reason why you have the distance. Okay, that's a high level idea. You are not really increasing the distance or like the correction power. Okay, anything that is error in your classical code will still be error here. Okay, that's a high level idea. So that's why you have a square of n. So now like we finished all the parameters, we prove it's valid, we prove it's bounded. Okay, so you may have the question like why it works and have any insights about like why they propose this kind of idea even at the beginning. Okay, so maybe that's the insight. Okay, here is like we are using the hypergraph product code to create the surface code. Okay, and the surface code we are just like combining with 2 repetition code. But the repetition code is not a very good LTPC code, but it's a reasonable code, right? And if you look at it, now like we have the first repetition code, they have n bits, okay? We have now like we are getting the tanagraph in a more straightforward way. And if you look at this one, this is a bits, this is a bits, this is a bits, this is a bits, and they are interleaved with checks, okay? So this is a repetition code, you understand, right? Okay, this is a repetition code. Okay, now let's look at how to generate the qubits. Okay, now let's look at surface code. Again, if you still remember, when we have both are qubits, you are generating a qubits. If both are checks, you are generating a qubits. Okay, if one is check, the other one is qubit, you generate a check. Okay, and that's why you have there, for example, the horizontal is this kind of this red checks, and this one is a green checks. You use the rules we have conducted, will get this graph. Okay, you add the connections. The connections, again, you propagate vertically, you propagate horizontally, so you get all these kind of connections. It will give you exactly the surface code. But now, like, we are rearranging these kind of qubits. Previously, we are putting yellow parts to one part, and the green parts, and the blue parts, and the red part to different part of the things. But now, like, we are getting this kind of information just as how they are ranging. Is that clear? On high level, okay? So on high level, it is that like one of the basis repetition code and when they hybrid, like you can having this kind of hypergraph together, it will create this kind of surface code. It allows you from the 1D dimension code to a 2D like quantum code, okay? But now like, because like you are still bounded by the logic qubits, so that's why you still have one logic qubits. And the distance is square of n, okay? So you have all the information similar to what you have for the HGP code, GP code. Any question? Yes?
Can I say that the tanagraph of the HGP code is just a Cartesian product of the tanagraph of the two classical codes?
So like the tanagraph
of the HGP code is a Cartesian product of the tanagraphs of the classical code.
I'm not very good at math in that way. So if you do the calculation or find it is, then it is. Okay.
It seems to be the case here, but I'm not sure in general.
Yeah. I think you can prove it. Okay. That may be a better unifying method. But after you have the unifying methods, it's better to think about whether you can give better code after the unification. If it doesn't really give you better code, then maybe you don't want to change the formulation in that mathematical form. Okay, and the reason why I'm giving the matrix format is because I want to use it for BB code description. Okay, and now the BB code is like after we have the HGP code, can we do better? And how can we do better? Okay, and it turns out that the BB code is starting from the initial step. Okay, how can we do the commute? Okay, it seems that commute is one of the critical information. At least we have to ensure it's valid. Okay, and we can ensure it's valid, and we can find the primary kind of component that will ensure both commute information and the degree information. Then we can easily generate a better code. So that's the high-level idea behind the BB code. Okay, so the high-level idea is like if you can write HX, the X-check matrix in this way, and the Z-check matrix in that way, yeah, you can easily see like if AB commute with each other, then it definitely commute. So it ensures that we have a valid code. So that's a high-level idea. Then the question is, how can we construct A and B? Okay, so AB should commute, and we have a way to really think about like what's the degree they're offering AB here. Okay, so in the next few slides, I hope I can give you some insights about why we are choosing the cyclic matrix as a basic component for A and B, so that they are both commute and they will have a better way to compute the degree. Okay, so let's look at the toric code first. Okay, toric code is very similar to the surface code, but the only difference is it's a parity code. Okay. So we are having like the checks from the end to the other end. Okay. So yes.
Oh, sorry, just a naive question. So the AB plus BA equals 0 sounds like they should anti-commute, or is it like equivalent whether they anti-commute or not?
That's a very good question. If you think about how this plus work, if the AB equals BA, they commute, they will also add to 0. The reason is they will be the same matrix. You're adding two same matrix together, and you are using, if you think about it, so they must have the same place at different kind of. 1 plus 1 always equal to 0. And so that's why like you always cancel out with each other. Okay. So if they anti-commute, they would also work. But here they commute, they will work too. Okay? If you think about that. Okay. Here the add is not the regular add. It's add to see like whether they have the same place for once. Very good question. Okay, so let's look at the toric code. Toric code. If you look at that, then you will find that this is by the HGP code. Okay, and by the HGP code definition, you will find that the HX and HG were in that format. Okay, it's kind of familiar. You always have this kind of A part and B part, but now like H, the H will be on different side because we're presenting like how they are propagated vertically and horizontally. And you get this kind of initial idea about A and B, but they are not perfect. The reason is if you look at H itself, it's just a cyclic matrix. Why it is a cyclic matrix? This one just saying like, okay, yes, you are checking on these two neighboring qubits, and this one is trying to checking the next group of neighboring qubits, and this one is like gradually like shifted to the right. Okay, so this is a cyclic matrix. Why cyclic matrix is good? It's because first, all cyclic matrix commute with each other. And soon, like I think you will see, like they can be written in polynomial terms, and the polynomial terms naturally commute with each other. And we'll see the proof very, very soon. But the first one is they commute with each other. The second one is they have a good control of the degree. Okay, it seems that now like you only have connecting like 2 bits. Okay, so having that, like okay, it also have good structure because it have this kind of practical like features of the because of this kind of cyclic matrix. And you may think like this one is just like a general case. You can have more like general like cyclic matrix. Okay, and this way like if you can control the number of zeros here, then you are control the degrees. Okay, so having said that, again like I promised you I will give you the polynomial terms. And here, if you look at a cyclic matrix, you can easily write it as identity plus different orders of this kind of basic primitive cyclic matrix. If you look at it, it's just like a kind of shift of the identity matrix. But now, like the cyclic matrix have one good property. That is, like it only has 1 rows, like 1 non-zeros in each row and one non-zeros in each column. So in this way, you have find the pure like terms, like basic small terms that both commute with each other and have a good control of the degree. Okay, you find that one, you may think, how can we build upon it? Okay, so that is the building blocks for A and B. You will find that actually you can use this kind of cyclic matrix and using their combination like the horizontal propagation, the vertical propagations to generate different orders, this xi and yi. Okay, in this way you are having the components. Yet again, like both x and y is in a good dimension, and you only have 1 zeros and 1 non-zeros, one non-zeros in each column and each rows.
The small issue is that.
Yeah, I think there's a typo there. Yeah. I think there's a typo here in this matrix, but you get the high-level idea. You are shifting to the right side, and you can break down into this kind of polynomial terms. Okay, and because it's polynomial terms, and you know that no matter what is the shift matrix, they always commute with each other, and you're getting this kind of basic component out of that. Okay. So now, like, let's look at IBM's BB code. IBM's BB code is try to, again, like for the A, they are getting like 3 A items, and B, they are having 3 B items, and for each of this A is a power of this kind of X and Y. Okay. And if you look at it, now A, because it has 3 items, the number of items in will control your degree. Okay, and both A and B, they will have a row weight and column weight of 3. The reason is you are adding 3 of them together. Each of this kind of X order or Y order will only give you 1 degree. Okay, so you are adding 6 of them together. So that is to see for each bit, for each qubit, they are connecting to 3 X stabilizers and 3 Y stabilizers. And for each of the stabilizer, they are connecting to 6 qubits. So that's a high-level idea. And the BB code will have their connectivity of 6. Okay, but definitely like you can, by adding different kind of items, terms here, to getting different kind of degree and have different families of the BB code. Okay. And especially like if you look at the BB code we are using in our previous paper, they are like 141, 12, 12, and their combination is using this different kind of things. For A, they have 3 items. For B, they also have 3 items. So that's why total you have the degree of 6. And definitely in their paper, like they try different kind of combinations, how like you control the L and N and M, and what kind of code you are generating, and what are the encoding rate, and also the distance, I guess, in their paper.
Can you explain what is X and Y?
X and Y. So X is this matrix, why is this matrix? They are building upon this kind of cyclic matrix. So they are basic component. Again, they only have two important properties. First, they always commute with each other, okay? And they commute with their different orders. For example, the x2 square, x3 square. They always, they have two groups. They always commute with each other. And the other important information is they have controlled degree. So that's why they are choosing this one as their primitives, okay? The primitives allow you to have the commute relationship and the degree information, okay? So that you can easily maintain the commute information between the x stabilizer and the x stabilizer and these stabilizers. But by multiplying how many terms do you need to have to multiply the degree, okay? So that, I think, is one of the key information in the paper. Yes?
Sorry, what is the subscript L? What does it mean here?
Okay, so if you look at the original, let me. So if you think about maybe here, it can give you a better idea about what is I and L means in HTTP code. If you think about it, is how many columns or how many rows do you want to propagate? Okay, even by itself it is. Then if you think about why we have on both sides, it's because you have this kind of 2D structure. Okay, and if you want to go deeper, you can read the paper to see how LM will affect the structure of the code. Okay, and you can have better visualization of the information. Okay.
Yufei, time check. So how much time? More time would you?
Oh yeah. I think we can. I don't have time to see my decoder. Thanks for a lot of questions. Maybe we can stop here. I think we have.
So you can take a few more minutes.
Few more minutes, sure. Okay. So.
We'll be on 10 past, no problem.
I just want to give you the high information of our decoder paper. Okay. Again, the current best decoder for our DPC code is based on BP and OSD. And if you think of the OSD is trying to, if you have a matrix, the reason why it cannot be solved is because the matrix have a lot of columns but not enough rows. Okay, that's a high level idea. And the OSD algorithm is trying to break this kind of code degeneracy by cut off some of the columns. Okay, but because you don't know which is the right columns to cut so that you can do the matrix inverse to get the result. So they have to try a lot of terms. And our method, try to build the decoder, if you think about it, is try to smartly adding more rows. Okay, like virtual check. Okay, by using this kind of virtual check, we can still rely on the BP algorithm, which is embarrassingly parallel and easy to implement and getting a good decoder. And if you look at it, we are implement our decoder on set of BB, GB, and GB code, and we show that, okay, the decoder, a good decoder first have to be ensure that we can correct a lot of errors, okay? And this kind of corrected error will give you a good logic error rate, okay? It turns out that our performance is pretty good in terms of the accuracy of the decoder. And the other one is the time efficiency, okay? If you look at OSD, one of the drawbacks is its time efficiency. It requires multiple iterations of the matrix inverse. And the matrix inverse itself is hard to parallel, okay? So that's why the OSD have some difficulty to generalize into our DPC code in large scale, okay? And our method is almost the same as a BP code because we only are changing this kind of decoding graphs. Okay, yeah.
What is OSD? Sorry, I know you are short of time.
OSD is order statical.
Post-processor.
Yeah, someone want to answer that question?
It's just order static post-processor.
Okay, it's
because it's adapted from a decoder.
But its method is try to find those columns. It's an abbreviation for after you run the BP, you will find that because of the degeneracy, you will find that some of the errors will not converge. And you run the OSD to resolve the remaining issue. Yes?
Sorry, I don't know if I missed it. What does BP stand for?
BP is belief propagation. And I think it's invented in 1963 for the classical decoder. And because classical decoder, you only have the trap problem, the circle trap problem, but you do not have the quantum degeneracy problem. So generally speaking, even though they are still theoretical, some cases, the BP code decoder doesn't really work. In practical, it works really, really well. Okay, so only last page. So if you want to play with the code, this is a QR code. You can scan it and you can play with it. It's quite self-explanatory. Okay.